This talk is mostly targeted to Java developers, and it's an overview of the current landscape of the JVM languages today, and some perspective that allows us to compare Java and Scala according to different facets that matter, and also contains a glimpse into what we should expect from future versions of Scala. Okay, so this is what the current JVM landscape, the JVM languages landscape looks like. Actually, I think I have this ruler for you to make it easier to see. So we see that in addition to the languages that we are all familiar with, like Java, JRuby, and Jython, which are basically just ports of these languages to the JVM, we have many more new players that are actually not very new at this point. Kotlin is not formally out, but it's actually an interesting language to look into. It's being developed by JetBrains, and it's probably the most similar one to Scala. One interesting point to note about it is the way that it handles nullability, which is actually more elegant. Kotlin is, you should expect it to be out very soon, and you should be able to start playing with it already. Ceylon is developed and promoted by Red Hat. It has some very interesting features as well. Groovy is a dynamic language that started more with the target of being very much compliant to the Java syntax, make it more dynamic and lightweight. The last release of Groovy also supports stronger typing. Clojure is a Lisp dialect that is basically compiled to JVM. Akamai uses Clojure, for example. So you see that that Scala appears here twice, and this is to make a point that in fact Scala is more object-oriented as well as more functional than Java, and it's more statically typed or type-safe. I think that the next slides will elaborate more and provide claims to support it. So this is who's using Scala. Obviously, you see that the Scala school and the tutorials are actually supported by Twitter, and most of the activity for these courses comes from Twitter. LinkedIn use Scala a lot, and Foursquare actually started with Scala from day one. Twitter actually had to rewrite much of their backend infrastructure from Ruby because of scalability issues. This is actually an interesting study that was done by Google. Oh, actually, this slide is wrong, but a different one shows that the runtime of Scala is very much comparable to Java, and in many cases faster, which surprised many. We see exponential growth in demand for Scala developers. And there were very interesting design trade-offs that were made in Scala in order to balance between expressiveness, performance, and complexity. Many, including me, believe that they really managed to get very close to the sweet spot. So the Scala is functional, object-oriented, statically typed, and compiles to the JVM, which also makes it interoperable with Java and other JVM languages as well. The man and the legend behind Scala is Martin Odersky. He designed Java generics, wrote the first Java compiler. Then he admitted many of the mistakes that he made with both of them and tried to fix them in Scala. Now he is both professor at EPFL, and he founded TypeSafe with the goal to promote the Scala ecosystem. I think that's a good a good segue to start exploring the cool features and the benefits of using Scala. So this is a class employee in Java. What we see here is a standard class with the fields and getters, setters, partial copy constructors, equals, hashcode, and toString. In fact, I added a few bugs here just to make a point. And also the first name and last name are swapped. The point is that the more code you write, the higher the chances that you have some bugs there. An equivalent class in Scala looks like this. And in fact, what you get here is all of these. So the constructor is basically generated by the compiler. Same for the copy constructors. The getters and the setters, you do not need to write the boilerplate, but you can do that if you want to override and customize the behavior. The equals and the hash code, the approach in Scala is actually very much more strict than in Java, because there is the equals hash code contract, which means that if two objects are equal, they must have the same hash code. This is not enforced everywhere, but all the collections and the case classes as well try to adhere to these constraints. I think that recursive decomposition is something that we will touch in a few minutes when we talk about pattern matching. Companion object is basically a static class or a singleton class that provides factory methods and other helper methods. This is what a singleton looks like in Java, and this is the equivalent in Scala, which means that basically the design pattern is now a first-class citizen in the language and has its own keyword. This also means that we can inherit and use all the object-oriented techniques that work with instances but do not really work with static classes. Everything in Scala is an object. It's something that you might be familiar with from Smalltalk and some other languages, which means that actually when I write 1 + 2, I'm actually invoking a method named plus on this object. It doesn't mean that behind the scenes we have boxing, right? It feels object-oriented, but it actually compiles to the same bytecode as what you would expect the equivalent Java code to compile to. But it actually allows us to do much more. For example, the plus operator, since it's an operator in Java, it's not even visible through reflection. And you can reflect the plus method in Scala because it's just another method. Another thing which is very important to remember and exploit is that there are no statements, only expressions, which means that every block returns a value. It's quite ubiquitous. For example, if returns a value, which means that we can assign the result of the if to a variable, and we can compose. So we get a much higher composability, which helps us basically make the code much more orthogonal and reuse the code much better. Same for for. Okay, so we see that for basically this collection, this expression creates a collection which is 2, 4, 6, and so on. Okay, we are basically applying the multiplication by 2 on every member here. Same here. Here we have a block. So every computation block returns a value. The last expression in the block is the return value. In this case, it's take the variable TMP and multiply it by 3. And same for, and this is actually the reason why we do not need to write a return keyword, because if the add function returns a value, then it basically returns this expression. We still can write return. I would say that it's maybe to make the transition to Scala easier for those who come from more imperative languages. But it's quite redundant, and quite quickly you will notice that you prefer to just omit it. We have a type inference in Scala. It is much stronger than the one in C#, but actually in Haskell they have a stronger type inference. For example, in this case, a variable, we do not need to specify the type, and the type is inferred. This is basically what we get from the REPL of the Scala console. Same for functions. In this case, since the compiler knows that y is an int, it will infer that the signature of this function, the return type of this function, is an integer as well. And the other example, the last example, shows us the least upper bound inference of the type. So in this case, we see that the least upper bound of a list and a set is an iterable. Okay? We have higher order functions in Scala, and a function is a first-class citizen, which means that we can pass a function as a parameter, we can assign a function to a variable, and so on. In this case, a very simple example, we want to add 1 to each one of those of the members of this list. So we basically define a lambda expression, lambda function that adds this value. We have a lot of sugar in Scala to make this easier, because these are very ubiquitous and frequently used. So we do not need to specify the type, since we have type inference. And also we have a placeholder notation that basically means that if we use a variable just one time, maybe it's too much of an overhead to give it a name, right? And we are actually polluting the code by thinking about a name and giving it a name. In other cases, it's actually useful because it helps us to document the code. But you can use your judgment here. An important principle is the universal access principle, which means that when you access a member of a class, and it should be quite transparent for you if it's a variable, a function, and what kind of a variable it is. This means that actually refactoring becomes very fun and easy. For example, if this class has a billion instances, and we do not want to waste too much memory on the members, so we just change the val here, which is a read-only or a constant variable, and replace it with a def. Then it becomes a function. That's all we have to do. Alternatively, if we want to cache the value, we can change the def to a lazy val. It will still be lazy, but which means that it will be computed only on the first time that this member is accessed. But if it's accessed for the second time, it will not be computed again. Okay, so you can just use all of these interchangeably, and it will be transparent to the user.